evolutionary process occurring with tree structures representing programs as we could have with just simple sequences of symbols. A nice compromise between the sort of linear string of symbols approach and the tree approach is something called gene expression programming. And that's basically built on the observation that in biology, there's two versions of an organism's information. There's the genetic information stored in its DNA, which is there, and then it gets turned into something useful for actually, for example, producing a protein or having some sort of effect in the environment. And that process of going from the linear representation in the DNA to the protein is called gene expression. And the important part about that is that not every part of a gene or a sequence of genetic information is actually used. There are large chunks of your DNA, for example, that are unused. We call it junk DNA, but it's not useless. It's actually a value judgment calling it junk DNA. It has a purpose. Its purpose is to act as a reservoir of diversity, because the coding and non-coding portions of a particular gene change over time according to certain mutations that might occur to the DNA. So in gene expression programming, we have a sequence of symbols and a set of rules that will take this sequence of symbols and turn them into a tree. But that sequence of symbols won't all be included. The non-coding portion is referred to as the tail, the coding portion is referred to as the head, and that dynamically changes over time so that the bits of the gene that weren't contributing can start contributing, bits that were not, and it basically allows us to spread the balance between two very important competing factors in evolutionary algorithms. And those two factors are exploration versus exploitation. And you do the same things with normal reasoning in your daily life. Exploration is where you generate options. So, for example, let's say you're looking for a job. You want to find out what jobs are available, or you're looking for a romantic partner. You want to find out what options are available. You can't spend all your time looking for jobs and no time actually doing a job. You can't spend all your time looking for potential partners and no time actually making something work. So exploitation is the other aspect. It's where you've got your job, you've got a romantic partner, you want to make this work well. So you need to spend effort on making it work well. And that balance between exploration versus exploitation is an important aspect in evolutionary inspired programming. We've done some work looking at switching between different strategies. So, for example, aphids, most of the time when things are well, they don't bother with sexual reproduction. They just produce identical clones to themselves because these clones do well in the current environment. But if something changes, so for example, the seasons change, they no longer do as well as they used to do. So they need to switch from sexual reproduction to, from asexual reproduction to sexual reproduction. So you may notice that you've got sometimes aphids, green aphids and then red aphids. That's an indication of whether they're currently reproducing sexually or reproducing asexually. So that's the basic idea at the sort of replicator level, and we're sort of transitioning now into looking at the organism level. So as I said, even very simple organisms are capable of expressing fairly remarkable amounts of intelligence. So slime molds are unsurprisingly, they're slime and they're molds. They're very simple organisms made up of single cells that cooperate together to perform fairly complicated tasks. So one thing they can do is that they can find food. Everything needs to be able to find food, but they can find food in the most efficient way possible. So they've been able to grow slime molds that will be able to find the shortest path between two points in a maze by placing food at one end and the slime mold at the other, and you'll see that it grows in a sort of breadth-first explosive exploration of the environment and then dies off, leaving only the connection between the food itself and the main bulk of the slime mold. So it's able to solve a maze without any brain, without any form of representation of what a maze is, but simply by carrying out a simple process, the emergent complexity solves the maze. Now, if we could look at some more sophisticated non-human intelligences, for example, the octopodi or octopuses, they are very intelligent. Unfortunately, they're very short-lived, but they're not like us in how their brains are structured. We're very centralized. We have a central nervous system. We keep it safe. We throw it all in the skull. Octopodi are more distributed. So they will have complex neural structures in their bulk, but they will also have separate mini brains, if you want to think of it, that control each of their limbs independently. So there's less of a centralized cognitive load and more spread intelligence throughout the organism. They're capable of solving very complicated tasks. So here's a puzzle where a small item needs to be maneuvered through a hole, and it requires a sequence of pushing and pulling. And if the organism were just doing random pushes and pulls, it wouldn't be able to maneuver the key through the hole. But the octopus is able to do it very well. It knows it's going to get rewarded. In fact, in aquaria, the octopuses are known for escaping their enclosures and going into other enclosures and eating the fish there. They need to be treated as like toddlers. They're quite intelligent. It's difficult to compare non-human intelligence with human intelligence, but they're definitely not simple. Even though, strictly speaking, they're a mollusk, the same family as snails. So it's amazing to think about. So basically, as I said, their intelligence is distributed throughout the organism, and this sort of distributed control can be seen in other things, for example, millipedes and centipedes, where each of their segments also has a neural structure that helps, for example, do walking. It would be silly to have a centralized brain that controls each of those limbs independently. Instead, what we have is a brain that sends a high-level instruction down the path, and each of the mini brains, other neural structures, then carries it out according to local conditions. And this is a good way for us to structure our systems as well. Central points of failure are bad in software engineering because if they go down, the whole system goes down. It's very good to distribute your control and intelligence throughout the environment so that it's more resistant to failure. This is one of the key benefits, for example, of the internet. The internet is a communication system designed to withstand nuclear war, and it's able to automatically route around damage so that after a brief period of lack of connectivity, if, for example, an important junction goes down, other routes will be found automatically and your connection will be restored. In fact, it was Edgar Dijkstra who developed that algorithm that we use. So if we look at if we look at the organism in a bit more detail, how is an individual organism intelligent? The cells aren't intelligent. The cell that forms our brains and our cognitive structures is called a neuron, and it's a fairly complicated structure. As you can see, all biological things are unnecessarily complex, but its basic job is to take in inputs and then decide whether or not or how much of an output to make. So we simplify that, and in machine learning, for example, we take a neuron and basically represent it as something that takes in a bunch of inputs and then performs a weighted sum on those inputs, and then passes that sum to what we call an activation function, which basically decides whether or not to send an output, or if to send an output, how much of an output to send. And that by itself is not intelligent at all. However, when we group them together, we get more intelligent behaviors. So this is what's known as a multi-layer perceptron network, and it's a very simple form of neural network, but it does count under the current way of naming things as a deep neural network because it has multiple layers. So basically, if we look at it from top to bottom, the top layer would represent the inputs into the system. So say, for example, you're evaluating the creditworthiness of an individual. It might be information about their current debts, how many payments they've missed, their age, whatever information you think might be relevant to modeling whether or not they're a good credit risk or not. If you look at the bottom layer, you'll see there's only two nodes. Those represent a decision being made, either yes, grant credit, or no, don't grant credit. Or if you're performing image recognition, is hot dog, is not hot dog, whatever it is you're trying to do. And in between, we've got fully connected layers, which will capture this input. So the basic idea is we feed in. We have a lot of data. That's the one thing that most of the fourth industrial revolution seems to need, is huge data sets. We feed that data into the first layer, measure the outputs, And if this data has been, for example, historically gathered, we can say whether or not that was the correct decision that was made. So we call that supervised learning because this is labeled data. And then we can measure how bad the neural network was at answering that question. And then through clever algorithms, for example, one called backpropagation, or through evolutionary algorithms, we can try and improve how bad this neural network is at measuring or at performing this task. And by feeding it lots of data and reinforcing the connections, weakening them or strengthening them, we eventually get something that can do the job we want. These days, we've explored more than these simple multi-layer perceptron networks. We've got much more complex cognitive architectures, and we're now in the field of deep learning. And this image, which is there, is basically the output of a certain kind of a deep neural network which has been trained on large amounts of different kinds of images and then given a new image as input, and then its sort of internal state has been visualized as an image. And you can see it's all sort of weird, trippy stuff where we've got dogs and fish and ducks kind of blurred into an image of what's clearly a set table. And this sort of isn't very useful, but it is an interesting insight into maybe if you could say that a neural network perceives anything, what's going on the inside of that neural network. That by itself was just merely a curiosity, but the real interest came when we started to have neural networks not working in isolation, but working together, or in this case, actually against each other. So a very important spin-off of these deep neural networks is something that we call generative adversarial networks. And this is where we take two networks. They're normally variations on a multi-layer perceptron network, specialized variations that reduce the number of connections between each layer. Because the problem with a multi-layer perceptron network is if you give it too much data, it basically becomes what we call overfitted. And that means that it, instead of actually learning anything, it's just learned to memorize the data set. And then you start giving it things that it hasn't seen before and it doesn't know what to do. Or, so there's a weird balance between overfitting, overtraining a neural network and leaving it general enough to cope with new data. And they found that by modifying the structure of those hidden layers between the input layer and the output layer, they can improve that. And some of these variations are called convolutional neural networks, and they're converse the deconvolutional neural network, which when paired off against each other form these generative adversarial networks. So the basic idea here is we don't want to classify existing images. We want to create completely new images that never existed before that have the essential attributes of the images we trained the set on. So the two neural networks are represented by generator and discriminator. One is a convolutional neural network, the other one's its inverse, a deconvolutional neural network. The generator's job is to make new images, right? And it does that essentially by drawing from random data. That's what that latent random variable input is, as well as we also feed into the system real images. The discriminator's job is to say whether or not the stuff produced by the generator is real or fake. And then we train both of them together. The discriminator gets punished when it's says that fake things are real and rewarded when it says that real things, that fake things are fake. And the generator's job is to try and trick the discriminator as often as possible. And with lots of data and lots of time, we have this. So there's a website called This Person Does Not Exist. Every time you go to that website, it shows you a new face. That is a face of a person who never existed in ever. But they've been trained on huge data sets and can produce new realistic faces. This has interesting implications when it comes to things like fraud, catfishing, anything like that, where you need to create online profiles that seem reasonable. But some people are sophisticated these days. They can detect fraud by doing a reverse Google search and finding the original image, but not anymore because now these people never existed. So for example, this is a whole sequence. I just ran it a couple of times. None of these people are real. Not one. Every time you visit the site, thispersondoesnotexist.com, it generates a new person. Some of them look a bit weird because at the end of the day, it doesn't understand what a person is. It's simply replicating patterns that it's seen. But none of these people are real. So that is something to think about, I think. Sometimes you can see weird artifacts in the background, but yeah, none of these people exist. Oops. Okay, so that's the cooperation between two neural networks. But the brain itself is made up of a whole bunch of different systems, and these systems are very specialized. For example, Broca's area is all about processing language, or visual cortex is all about processing images. How do these different areas get specialized in your brain? So one sequence of or school of thought was about trying to replicate that process itself. And Kohonen, a Finnish computer scientist, created these self-organizing maps, and they're considered a type of neural network, although I disagree, but that's a personal opinion, a value judgment. But the basic idea that you can think of them is, let's say you've got a really complicated scene in front of you, and you don't want to represent that scene perfectly. You just want a summary of that scene. So look at the table in front of you, and you'll see it's covered with all sorts of nonsense. If you were to throw a cloth over that table, it would capture the general shape of the nonsense that's on your table without you having to know exactly everything that's on the table. So that's the basic idea for a self-organizing map. And here's a demonstration of a self-organizing map learning a pretty flat sequence of data. So basically, it's going to look like a rolled up cloth that's going to gradually flatten itself over data that gets added continuously. So here we go, blah, as time goes by. So the basic structure of it is it's normally in a grid, or either a rectangular grid or a hexagonal grid. And every time you feed a new data point to it, the closest intersection in the lattice is found. It gets tugged towards the data point, and everything that it's connected to gets tugged along with it. So you repeat that process indefinitely, and you gradually taper off the strength of that tugging, and eventually you get something that will capture the high-level features of the data set with a limited amount of points. So the point is that you can capture the shape of data with a much smaller data set. So I'm now going to be dumb/brave and do a live demonstration of a related but different approach called growing neural gas, which also works on basically tugging connected nodes together as you feed it more data. But the point is that we can add extra nodes when the tugging is successful and lowers the overall error. And we can, whenever a node gets tugged, everything that's connected to it also gets tugged. But when tugging doesn't happen, the connections start to weaken. And eventually they break off. And if a node gets isolated by itself, it disappears. So we've got a system here where new nodes get added dynamically, and new connections get added and removed dynamically. And it basically allows us to do two interesting things at once. Let me bring it up, and hopefully it will work. So it'll be easier to see with an image. If this is slow, if anyone is sitting on a committee where they decide on what the maximum level of hardware we're allowed to order for our laptops is, you're welcome to use your influence as you see fit.
This is the second time an academic is sitting.
Okay, so I'm just saying. Okay, well, while we wait, it will eventually come up. I've got some stuff. This is one thing about machine learning and so on, is that it's very data driven. So it does require quite a lot of hardware. Okay, well, while it's doing that in the background, I will show you the basic idea in images. Why is this not? Those were hidden. Okay, from current slide. So the basic idea is that we will generate a sequence of data points. There will be some inherent bias in the data in that there will be clusters that naturally form. The algorithm doesn't know anything about these clusters, and it will grow over the data set doing two things. One, it will allow us to find data points that are fewer in number than the original data points, but still capture the overall shape of the data. And two, the connections will break off between the different nodes, allowing us to what we call cluster the data points. Basically, anything that's connected to each other still after a certain point, we can consider to be part of the same cluster, and we can find all the data points that are near those subgraphs that form, and we'll have both summarized the data as well as clustered it. And hopefully, yeah, my thing is up now. So let's bring it up. So here we've got our data sets. Something that looks like it'll be fun. And we'll start running the sequence. You can see it starts off with 2 nodes. Those can never be isolated. New nodes will be added dynamically. New connections will be added dynamically. They'll be pulled towards the data. So you can see it sort of has an almost biological look to it as it sort of reaches over the data set. We should start getting soon. Yeah, there we go. Don't know why it wanted to be too circular. We should get colonizing the various clusters, and the connection should start breaking off between the nodes as those particular ones don't get tugged. And then eventually it will have colonized all of the data, and we will have clustered it as well as summarized it, or found points that can be used as the basis of creating a summary of the data. So that's the basic idea. I think we don't need to run it until it's fully concluded. Please note this is like a multi-agent system, so it's still running in the background. The visualization actually doesn't control it, so I need to kill it in the background as well. And good to go. Now we can carry on. So that's what's called growing neural gas. Again, a poorly named algorithm, because I suppose it's gas-like in the sense that there's sort of stochastic movement, random movement, and it's neural in the sense that stuff's connected to each other, but I don't really agree with the name, but it is what it is. All right, the other level of intelligence that we wanted to look at in the organism is that of the artificial immune system, or of the immune system. So the vertebrate immune system is adaptive. You've actually got several immune systems. Even your skin counts as a barrier as part of the immune system. But the interesting part of the immune system is the adaptive one, the one that adjusts to things that it hasn't seen in ever, because there's so many possible things that could hurt you. It's impossible to have a perfect record of all of those things. So your innate immune system stores responses to things that your ancestors and their ancestors and their ancestors dealt with, and it doesn't change very much. It very slowly changes over time. But your adaptive immune system changes during your life, and there's various immune cells that get created. One of the simplest subsets of that is you've got these cells that can recognize antigens, but they don't, or pathogens, things that cause harm, but they don't know whether they're responding to something that's genuinely causing harm or whether they're responding to part of you. So a big part of the learning process for the adaptive immune system is to learn not to destroy yourself. There's a lot of diseases that come from your immune system attacking your own body, and that's where it's incorrectly learned that certain proteins or parts of you are bad and should be attacked. So this is called self-non-self discrimination, and part of recognizing that is something called, let's say, for example, danger theory, where when something bad happens, like you're injured or there's a tumor or something like that, your danger signals will be emitted. And if we've got a response to that in addition to the danger signals, we have a better indication that the thing we're responding to is actually bad because it coincided with those danger signals. This is a picture of the major histocompatibility complex. It's actually unrelated to what I was just saying verbally, but basically part of our immune system needs to look at what's going on inside cells. We can't see what's going on inside cells if they've been invaded by a virus or something like that. We don't know from the outside. So we need to be able to see the internal contents of cells. So basically we've got these cells that gobble things up and then expose what they've gobbled up, the contents of what they've gobbled up on their surface. Those are called antigen-presenting cells. And the major histocompatibility complex is kind of like a summary of what was consumed by the antigen-presenting cell, and the actual sensor and effector cells of your immune system, your T cells and your B cells and all of that, can then read that and carry on further. So the immune system is stupendously complicated, and there's all sorts of aspects to it. And we've taken some aspects of the immune system and summarized them and turned them into algorithms that may or may not be useful. Very simple one that is proven to be quite useful is negative selection. It looks at that part of the immune system which tries to learn the distinction between self and non-self. And basically, you generate a whole bunch of detectors. Those detectors get fed, or the data set gets fed to those detectors. Ones that fall within a certain radius are counted as having detected them. We've got the data set pre-classified as being self, non-self, whatever the two categories you're trying to discuss is. And our job is to try and move those detectors around so that they don't classify self, and they do classify non-self. Positive selection is actually a bit more like the evolutionary algorithms we looked at earlier. We've got a whole bunch of cells that are generated, lymphocytes that are generated that respond to something random, and those that actually get exposed to something in your body. So if you've got in your marrow, your body produces all sorts of lymphocytes, and they're randomly coded. There's a portion of the lymphocytes DNA called the variable coding region, which mutates very, very quickly. So it represents what the thing can detect. But most of the detectors won't detect anything meaningful. But if a pathogen is present and a detector detects it, that lymphocyte gets duplicated. It's called clonal expansion. And some of those lymphocytes have their lifetime extended dramatically. They become what we call memory cells. And those stay in your system. And then if there's a future occurrence of the same pathogen, they're there to detect it. And that's why your immune system learns over time. So that was artificial immune systems. So that's at the individual organism level. If we now look at cooperation between organisms, we come into the aspect of multi-agent systems. So multi-agent systems are a way of building software. By themselves, they're not artificially intelligent at all. Basically, it's a way of structuring your software so that it detects things that are going on in the environment through sensors, a sequence of percepts we call it, and makes changes to the environment through a sequence of actuators. So the basic job of the agent is to map a sequence of percepts onto a choice of action. And there's different ways of doing it. Simple reflex ones just have a fixed rule that gets applied. Model-based ones will try and build an understanding of the environment and will base their decisions on that understanding. Sometimes that understanding gets updated, in which case they're considered to be learning agents. Some have high-level goals. There's many, many variations. But let's take a look at a fairly simple one called Boyd's, which is used in movies quite a lot and computer games. And its job is to make a simulation of flock and school formation. So if you're in a movie and then there's a great swarm of insects or a great swarm of birds or a big crowd or something like that, you don't want to have to simulate at a very high level of detail each one of those entities in the flock. You want them to behave convincingly as a collective and do the minimum amount of work computing the decisions for each of the members of that flock. So Boyd's algorithm, developed by Craig Reynolds, is very simple. Basically, every Boyd or bird looks in a looks in a sphere around it, and it sees what the center of gravity is for the other birds that are in its environment, then moves towards that. So that's sort of converging behavior. But it doesn't want to crash into its neighbors either. So the neighbors push it away. So that's an avoidance behavior. And then they all want to align together to move together. So there's sort of an alignment behavior. And it's all done with very simple vector mathematics, which can be optimized quite efficiently. And the combination of these three rules is enough to do obstacle avoidance and moving towards goals and all sorts of stuff like that. So here's an image from the 1980s. It's actually, this particular one is from a course in the 2000s, but this footage was created in the 1980s. Moving the Boyds through a virtual environment. They can avoid obstacles. They can go around complex obstacles towards goals. And all of that simply by applying very, very simple rules. It's the emergent behavior of the collective which has the quote-unquote intelligence. Another kind of emergent intelligent behavior is that of social insects. So ants move around and they do complex things like building anthills and finding food and doing stuff like that. And the way they do that is by modifying their environment temporarily. It's called stigmergy. So basically, as an ant moves around, it lays down a trail of pheromones, which are hormones external to the body, right? So if you want to think of it like that, which can be picked up by other ants. And if an ant finds food by randomly wandering around, it goes home, but it lays down a trail as it does so. And other ants are more likely to follow that trail than not follow a trail if they haven't actually found food or aren't doing anything more important. And over time, that trail gets reinforced, and ones that don't lead anywhere fade away because the pheromones have a limited lifespan in the environment. So these trails get laid down leading from the ant's hive, anthill, to food and water and various other important things. Likewise, ants and termites have different roles like soldier and a forager and so on. How does an ant decide what role it should fulfill? the queen doesn't coordinate anything. The queen isn't like some sort of central intelligence for an ant hive. The queen is an egg-laying machine. That's the job of the queen. It's more like an organ than a brain. But for example, to decide what role an ant should play, they simply count how many times they've encountered other ants fulfilling that role, and they have an internal representation of how often they should be encountering other soldiers or other foragers or whatever. And if they don't encounter them, maybe the soldiers all died off in a battle, then they will switch to becoming that, and there'll be physiological changes that accompany that. So a useful application of ant optimization is where we want to cluster a graph. So a graph, you've seen them before, but they're connected nodes like a network, but sometimes you want to split them into subgraphs according to their natural decomposition, kind of like what we did with clustering the data just before with the growing neural gas. We don't want to decide in advance how many clusters there are. It wants to be exposed naturally. So one thing you can do is you can have ants run around the virtual ants run around the graph every time they transition across a connection. They reinforce it. Every time that doesn't happen, it gets weakened. And over time, the graph will decompose into its collection of highly connected subgraphs, and you've got a useful decomposition of the graph. One last thing to look at is a completely different kind of social insect intelligence. Not all ants modify the environment with pheromones. There's a very simple kind of ant that literally has one-to-one communication between two ants. So if an ant has found food and it wants to tell another ant about it, it literally grabs the other ant, emits very localized pheromones and points the ants in the right direction, and off the ant goes to find food. It's called tandem calling. And there's an algorithm based on that called stochastic diffusion search, where basically if you've got a problem that you're trying to solve, it needs to be decomposable into individually solvable subproblems that can be measured as being successful or unsuccessful. If you're successful, you stay working on that subproblem. If you're unsuccessful, you make yourself available to be recruited to work on other subproblems. An easier way to think of that is to think about going to a restaurant. So let's say you're at a conference and you've got a whole bunch of dining options, and there's people with you from the conference. No one really knows the city because it's a conference. So you all go to random restaurants, and the next day you report to each other whether you like the food at that restaurant. If you like the food at that restaurant, you just go back to that restaurant again and order another thing from the menu. But if someone was really unhappy with their order, they will maybe go to a restaurant that someone else went to that did like it, right? That's the equivalent of the tandem calling. So eventually, over time, you'll see that the good restaurants have more people going to them, and therefore you can identify the good restaurants simply by this process of exploration. So here's a live demo which may or may not work. It wasn't originally meant to be visualized. So hopefully on this smaller version of it, we'll still see the correct behaviors. But basically, often in solving these problems, you represent your solution space as a surface. So let's say you're trying to solve an optimization problem between two competing variables, you can represent that as a plane. Or if you want to solve it, with higher things, you can represent it as a surface or weird higher dimensional shapes that we couldn't visualize. So over here, we're going to look at a very simple surface. Let's say one where there's absolutely terrible solutions in the middle and only good solutions at the edge of the parameter space. So there's going to be this deep pit in the middle. And what we hope to see is our solutions clustering around the edges. Good luck to us all. Okay. All right. So, it doesn't look so great from that edge there, but if we look at it, so there's really terrible solutions in the middle, and over time this thing resets after a couple of seconds, so it doesn't run continuously. You'll see when everything disappears and it redoes it, but hopefully you can sort of see that the solutions are clustering around the edges of the solution space with some random ones winding up in the middle. So it does kind of seem to be working. And let's do it again. Okay, sorry, this is not going to close nicely, but it's the last thing, so let's just run it again and do one where there's a good solution in the middle, and then okay solutions elsewhere. So that's often a problem you have, is there isn't one great solution. There's a bunch of okay solutions. So, and sometimes you don't actually want to take the best solution, because human beings, when you're representing your problem as a surface, you have to encode everything about the problem in the surface. But in reality, the decisions are made that take other stuff into consideration. So let's say, for example, you're talking about whether you should hire or fire people, right? And the amount of people you're going to hire or the amount you're going to adjust wages might be the inputs to this parameter space. So In reality, you obviously want to do the thing that's best for the company that maximizes the company's savings. But in practice, you have to deal with actual people, for example, labor unions and so on. So you might want to also know what the less good compromise solutions are as well. So this particular algorithm will find, hopefully, the good solutions, but also explore the solution space properly to give you candidates options elsewhere in the solution space. This is the sombrero algorithm, sombrero thing. It's got one good solution or a concentration of good solutions in the middle, and then a lower ridge of lower quality solutions elsewhere. And kind of looks, it's definitely exploring the solution space properly, and does look like it's clustering around the perimeter of the good solution and then climbing up the good solution. It's hard to tell, so I don't know if you think it's running long enough before it resets to fully explore it. Whoops. But that gives you the general idea about how this might work. So just one last note on good solutions versus bad solutions. So we often refer to the good solutions as being part of what's called the Pareto optimal front. So basically, if you're combining different trade-offs, you want to be in a situation where if we trade off on one thing, it benefits the quality of solution until you reach the point where any trade-off in one thing or the other will lower the overall quality. So that's what we call the Pareto optimal solution. So hard to understand with that description, but easy to understand with an allegory. So let's go. Let's say, and I just want to also say that Pareto optimal solutions aren't fair. If you've got let's say you want to make people happy. You've got a bunch of people who've got no money, and you've got all the money, right? And you want to take a decision that doesn't hurt anyone and helps at least one person, right? A Pareto optimal solution would be to take the money and give it just to one person. No one was harmed, and one person benefited. But it's not the fair solution, because the fair solution would be to at least help as many people as you could with the money that you've got. So there's a big difference between optimal solutions and fair solutions, unless you can somehow encode fairness in your solution landscape. Thank you very much. Oh yeah, questions.
Yes, any questions? We've got one here.
Hi.
So, Duncan, I absolutely love that. It was very, very interesting. So, you said in the beginning, if I got you correctly, but I might have gotten you completely wrong, you're not trying to recreate intelligence as in the human form of it, the higher definition, I think is what you called it.
Strong intelligence.
Strong.
Yeah.
You're doing the weaker one. So, just for interest's sake, are we as humanity making substantial progress in the stronger one?
I don't know. And it's a great question. And there's a lot of people who fear creating. So like a strong intelligence is something that can do everything humans can do, but better, right? And the big fear about that is that, well, one of the things humans can do, apparently, if they can create a strong intelligence, then that's something that they can do. So clearly, a strong intelligence is better at creating other strong intelligences than humans. And the fear, it's called the singularity, is that once that happens, the next one makes the next one, makes the next one, and you've got this exponential curve asymptotically approaching infinity, and eventually you've got some godlike superintelligence, which is nonsense. Well, I don't know that for a fact. So my qualified opinion is I don't think that's the case. It is probably possible to create a better than human intelligence, because it's unlikely that through random evolution, humans are the best solution to being intelligent. Evolution gives you okay solutions, ones that are good enough. It doesn't give you the best. So there might be a better than human intelligence architecture that could exist, but it's not an asymptotic curve off to infinity, because as I've hopefully has come across in my talk, intelligence arises where you've got connectivity between different things. So the two neural networks in a generative associative network, the cooperation between the ants and the birds, and all of those things. It's that cooperation that causes intelligence. So wherever you've got cooperation, you've got communication, and wherever you've got communication, you've got congestion. So basically, there is a limit to the amount of connectivity. You spend a certain amount of time communicating, and that's time spent not thinking. So what looks to be the beginning of a curve asymptotically going off to infinity is probably the beginning of an S-curve, where when you reach some critical point where the cost of communication between components exceeds any benefit that you get in overall intelligence, it should level out again. It may well level out at a point higher than human intelligence, but it certainly wouldn't be godlike intelligence. The thing is, we don't, and just to be extra weird, intelligence isn't the same thing as consciousness. We don't know what consciousness is. There are many intelligent processes that are clearly not conscious. We've shown you those. And even in a human being, you can get intelligence without conscious awareness. So, for example, people who have their corpus callosectomy, the connection between their two brain regions severed. You can show one half of the brain, one eye, because each half of your body is controlled by a separate hemisphere, an image, and the other side will, like, let's say, for example, you show one a picture of a dog, and then you ask the other hand to pick up, and there's a barrier that stops this eye seeing what that eye is seeing, and you ask it to pick up a random toy, and it picks up the dog, and you ask it, why did you pick up the dog? And then the brain does what brains do, which is called confabulating. It lies to itself, because the job of the brain is to tell a series of lies to yourself to explain why you are where you are. And the person will say, oh, I just always liked dogs. They'll have no conscious awareness of what the other side of the brain said. So severing the corpus callosum doesn't, like, the brain is still connected through the hindbrain and other places like that. So there's some connectivity still, but there's no conscious awareness of what the other side is seeing. So, and only one side of your brain controls language. So that's the side that answers. So it creates very disturbing implications about what the nature of self is. So we may well get superhuman intelligence long before, if we ever get artificial consciousness. It is actually a separate problem.
Okay, so sorry, I just want to come back to you on that. It's. I've read, and once again, I might have read a mistake, but that the human brain is the most complicated object that we are aware of in the universe as a single object,
I think,
as a network.
I think so, because there are these sort of layers of complexity. So what they're talking about is the connectome. So you've got the individual cells and things that make up the brain, and they're obviously very complicated. But the real complexity comes from where different bits of the brain connect to each other. And that's hope, maybe, where whatever it is that is you is stored. So just like in that multi-layer perceptron network, we had those links between the different layers. The weights of those links are where the information is stored. The connectivity between different cells and different regions of the brain is where information is stored. And that's really complicated, yeah.
Okay, so I'm going to make a last comment, because I would spend the whole day with you,
Okay.
because I'm very interested in this stuff. It's fascinating. But I really think you should write a popular book explaining some of this. And the reason I say that is because what you've said today, not that I've been afraid of the future, but when you think about artificial intelligence, it's difficult to know where it's going, as you've mentioned. And I think what you've done today is just shown up that it's a much more complicated business than we think in our popular minds. And I think it's something we should all understand a little bit better. So thank you.
Okay, well, just to respond to it, I've got two fears about artificial intelligence, but they're not the fears that you probably think. It's not a fear of some godlike AI, and it's not the fear of, the robot uprising. My one fear, and I think it's very realistic, is the popularity of machine learning at the moment is leading a lot of people to engage in machine learning and make decisions based on machine learning without understanding the limitations of those algorithms. People believe the decisions that are made, for example, by a recommender system because the computer says so. And they may take decisions that affect real human beings based on what the computer said. And no one in this decision chain actually understands the underlying algorithm and its limitations. So I think that we're actually already there. That's a problem. The other problem is growing complexity. So even if you just look at something which takes a while to change, which is laws. So if you take, for example, the tax law in the US, the tax law in the US is being added to at a rate faster than a human being can read. So you could sit down and read every day, all day, and never understand the tax law. So the danger is that, and that's tax law, is to say laws take a while to actually change. The danger is that we could wind up in a situation where the world becomes so complex that it is impossible for an unaugmented human being to engage meaningfully in society because it exceeds the sort of computational threshold that a human being can meaningfully participate in. That's probably not such a big problem because most of the time we don't know what's going on and we're fine.
Thank you, Professor. Yeah, after that, I feel like I need to check if everything about me is even real. But our next speaker is the current head of department in chemical sciences, and his main research interests in heterogeneous catalysis rather. And he has been intrigued by the potential of open source hardware and distributed manufacturing. And his lab has several 3D printers and is producing various pieces of hardware for research and teaching. Ladies and gentlemen, to speak to us about imagining, please help me welcome Professor Reinout Meiboom.
And you help with the video, right? Okay. Is the mic on? Can you hear me? Can you hear me at all? You don't hear me? Is it perfect? Okay. Fantastic. Let's start. Imagine, ladies and gentlemen, a world without hunger. A world where everybody has a house. A world where medicine of a rare disease gets produced right where we need it. Wouldn't that be fantastic? Reality obviously is different. This is the front page of Time magazine of May this year. And I think a lot of people with me woke up seeing this picture, being horrified. South Africa is the most unequal country in the world. This is in Johannesburg. I live here. And we've got a posh neighborhood right next to a squatter camp. That's not a good situation, ladies and gentlemen. But this is caused, in my mind, by a thing called artificial scarcity. Right? Artificial scarcity basically means we have the means to produce what we need, but somebody's making a profit. And because of the profit, we have other people living in poverty. Now, some of my colleagues think I'm crazy, the rest of them know I'm crazy, because I'm asking silly questions like this. Why are people hungry in Johannesburg? Right? City Parks tells us we've got 10 million trees in Johannesburg. If you look outside, it looks more like a forest than an actual city. So the question, why are people hungry in Joburg? Right? Let me change that question. If every tree in Johannesburg were a fruit tree, the average apple tree produces between 80 and 150 kilograms of apples. With 10 million trees, you can do the calculations, you could feed 5.5 million people for free. Right? Joburg only has 4.5 million people, so we could help, I don't know, Limpopo. Right, so what I'm trying to say with these examples, ladies and gentlemen, is we have a number of problems, but we can solve them, but only if we think completely different than what we've been doing in the past. Good morning, everyone. My name is Reinout. I'll put it on here so I don't forget it myself. I grew up in Holland. I was raised in Holland. For those of you who don't know where Holland is, if you take the N1 towards Pretoria, and you continue for another 13,000 kilometers, you get close. Right? But I came to South Africa as a tourist, fell in love with the beautiful country, the beautiful people over here, moved in and decided to make a career. So I started my career at UJ, applied for a research grant. The grant got approved. Fantastic, fantastic news. I got a grant, and then you read the fine print and you realize you only get a quarter of the money that you need. Then you've got a problem, right? Because I'm in chemistry. Chemistry is expensive equipment. And with half of the money or a quarter of the money, you can't really do all that much. At the same time, I get my students coming to me. Prof, I'm hungry. I'm hungry, can you help me? So I sat down and I thought, we need to do something. I started a project, both in my lab as well as in the neighborhood, that are called the Freedom Baker. It's inspired by the Shuttleworth Foundation's Freedom Toaster. And the idea is just if we provide relatively cheap hardware, then we can bring the price down of a loaf of bread. As simple as that. The students tell me they're hungry, so I got them a simple bread baking machine. And if you do the calculations, you pay about a quarter of the price for a loaf of bread as compared to the nearest shop. Right, and these are yesterday's prices. I had to Google what the price of a loaf of bread is. We've got one of those machines at home, but we don't eat bread. We just bake bread for other people. By now, the machine has been baking a bread every day for the last 4 years or so. So the actual investment of the machine has come back time and again. But what if we can go better? This is only a reduction of 75%. What if we can reduce the price of everything, by 99%? It involves doing a little bit, but rather than paying 100 rand, you pay 1 rand. And what would you do with the other 99 rand? Right? Obviously, you can't buy 100 loaves of bread because they'll go off. Is this possible? And I think, ladies and gentlemen, this is possible. We're going through something of a revolution. People call it the fourth industrial revolution. I'm talking about a completely different part from the previous speakers. I'm talking about an open source hardware revolution. This is driven by the internet. It's a tremendously exciting prospect. And I will show you, or try to convince you, that this actually works. Incidentally, I took a beautiful French painting about the French Revolution. The only reason is if you look for pictures on the internet about revolutions, it's all politically connected, right? So to prevent anyone from thinking I'm a communist or one of those other revolutionaries, I just took this beautiful painting to illustrate the point. So what is happening? We've got an open source hardware revolution going on. I'll go and explain 4 concepts that are necessary to understand. After that, I'll show you a little bit of what we are doing, and then I'll come back to my initial statement of can we get rid of poverty worldwide? Right, so the 4 concepts that we need to look at is distributed manufacturing, which is pretty much a key aspect of the fourth industrial revolution. Digital manufacturing, it's related, the two. Obviously, we need to talk about open design and circular economy. Once we understand those concepts, we can have a look at what we're doing right now over here at UJ and then expand on the possibilities that are out there. Right, so the traditional way of manufacturing is you put down a huge factory somewhere, ship all the starting materials to the factory, do whatever you need to do to get a product, and then ship the product back. Right? One of the strangest examples that I can think of is over here in Rustenburg. There's a platinum group metals mine. The platinum group metals get mined, they get shipped to England, they get refined in England, and they get shipped to Germany, where a compound is made, and then I buy it, that compound from Germany, over here in Joburg, and we're not even 100 kilometers from the mine. Right, so that's the central current state of production. In this little picture, there's a factory in China on the left-hand side, but the idea you get is we've spent a tremendous amount of energy and pollution on shipping things around. If, on the other hand, you have a small factory everywhere, regionally, right, and this can be seen as a factory servicing a country or a province or Joburg the Joburg municipality, or even a house, then you don't have all the shipping around and the distribution and the waste around centralized manufacturing. Right, so the simple, silly example again is the nearest baker probably has large equipment to bake 100 breads. They bake 100 bread, but can they sell all 100 of them, right? Maybe they sell 90, and what do you do with the leftover? If you have a silly baking machine at home, the moment you're hungry, you throw in your starting material, and the thing bakes it for you. You actually don't have to do all that much, right? And that means that there's a reduction in waste. And similarly, every production situation can be handled. Digital manufacturing, and these are just 3 examples of digital manufacturing, is typically where you take a computer file and stick it in a machine, and the machine does exactly what you want it to do. Right? And this fits in with the distributed manufacturing, because all of a sudden, the lightest part of the production process, the file, can be distributed via the internet. The example here is of an open source 3D printer. It's a relatively cheap piece of equipment, and this is even one of the more expensive ones. It would go right now for about 10,000 rand, but you can get 3D printers for 2,000 rand. Right, so it's affordable. On the right-hand side, we have 2 open source CNC machines. The top one could machine aluminium. The bottom one is large enough to fit a complete piece of wood, the standard size that you can buy it. The reason these have different prices, 2 numbers, is simply if you have access to 3D printing, you do not have to purchase the 3D printed parts, right? So only the electronics, etc. And basically, again, for less than 10,000 rand each, you could have one of those. We've got about 4 of the 3D printers in my lab right now that have not been standing still since they arrived. They are working continuously. Pretty much everything can be manufactured digitally. This is an open source digital knitting machine. So if you think it's cool, you tell your knitting machine, knit me a beanie, and then you go to work, and by the time you get home, you've got your little beanie to wear. For those who don't know how 3D printing works, and now this is the technology part. This is a short video of one of the printers in my lab. So as you see, it takes a layer of plastic, puts it down, moves up a little bit, puts a new layer of plastic on it, exactly according to the model that you want to have. This, incidentally, is a model of a carbon atom that we use in a model kit that we hand out. And we'll get to that a bit later again. The next part is open design. Open design basically means if you design your object, your file, then you can decide what copyright you want that file to have. And there's a large group of people that decide they don't want any copyright on the file. They want it to share it with everybody worldwide. And it typically gets uploaded to certain databases. Thingiverse would be one of those databases. And the advantage is that everybody can download the file, print the object, or cut the object, or make the object. And then you get a lot of people looking at the same design. And on the right-hand side over there, you see, for example, a syringe pump that was designed a couple of years ago. And it went through a number of iterations, a number of different designs very rapidly because a lot of people look at the file. Now, this might sound very strange to a lot of us, but those of us in academia do exactly that every single day. We do our research, we do a lot of work, and once we've brought the research to a conclusion, we write it up and we give it to the world. Right? We call it publication in a journal, but it's actually, we've done all this work and we give it to the world for everybody else to benefit from. The same thing is happening with the open source hardware and the open source software, obviously, which this is derived from. Finally, we need to look at something called the circular economy for a very simple reason, that once the resources are somewhere, we need to keep them there, we need to catch them. But the traditional linear economy that we're all completely used to is mine a resource somewhere, do something with it, build an object, ship the object to the other side of the world where somebody buys it. And once, in this case, a chair, once the life cycle is done, we throw it away and we ensure that the landfill gets filled. Right? If we look at the circular economy, then obviously we want to reuse these things, give it to somebody that can use it, or we recycle the starting material so that we can build more objects with it. And only the last resource is disposal of the starting material. Now, this is very similar to what a lot of people have been preaching, and this is an advertisement for a glass company.
Recycling 1 glass bottle saves enough electricity to use a lamp for over an hour. Recycling 2 saves enough power to make toast. 10 to watch your favorite soapy. Recycling 30 tons saves enough energy to power a suburb. If everyone in the country recycled just 1 bottle a month for a year, we could light up Joburg for an evening during peak hours. Imagine, one day it might be possible to recycle enough glass to light up South Africa. The Glass Recycling Company.
Imagine that. Recycling your glass can save enough electricity to light up Joburg. Right? I don't know about you guys, but I drink more than 1 bottle of wine per month. Right? So we could actually save a tremendous amount by keeping the resources in the economic loop in this way. But it's not just glass. This is just an ad that fits in nicely. It's not just glass. There's an open source project in Holland, Precious Plastic, that's all about recycling every bit of plastic around. Right? They've got a shredder to shred the plastic into small pieces. Then they designed a filament maker, so these things make filament for 3D printers. You can do injection molding, and this could close the loop on the plastic around us. Just imagine going around the street and you find all these plastic bottles. It's all the same material. You can shred them, you can turn them into a filament, then all of a sudden the going price for that filament for a 3D printer is approximately 300 rand per kilogram. Right? The bottles that we see every day on the side of the road. Then with a 3D printer you can make an object, and in this case this is the wonderful bust of Nefertiti that I've got over here. Just imagine how you could teach history students using these objects. And obviously, by the time you're done with that one, you just shred it and you make new filament of it. Right? So we could start a complete circular economy right here, right now, because the equipment is relatively cheap, right? 3D printer would set you back anywhere between 2,000 and 2 million, depending on what you want. But this filament maker has been published about 2 months ago, open source, and it would cost you 3,000 rand to build one. Again, you do need to put in a little bit of effort, but it's well worth it. Right, so everybody's seen these type of pictures about the fourth industrial revolution. I just wanted to put a 4 in this presentation somewhere as well. But the idea is really digital, distributed manufacturing. Right, and the moment we get that sorted out, we can actually go on and help people. Right, so what is it we're doing in the lab, in the chemistry department right now? We started off with 3D printing, and we started off actually building these very simple molecular modeling kits for the students. And the reason is very, very simple. On the left-hand side, you see a molecular modeling kit that was the cheapest I could find online from Banggood, so it gets produced in China, and that costs 200 rand. That is too expensive to give every first-year student. But when we do the calculations and we produce these kits ourselves, it costs us less than 8 rand, right? So all of a sudden, we reduce the cost with about 95%. And now we can hand out these kits to all our first-year students. 200 first-year organic chemistry students receive a 3D printed kit, and they can understand the molecular geometry. Nice thing is, there are other models. This is a space-filling model, for example, and I'm going to do a little bit of chemistry. A carbon-carbon single bond rotates, right? But a carbon-carbon double bond doesn't rotate. This is the same kit. See if you can rotate it. Right? It does completely the same modeling kit. One print. What else is possible? We print all kinds of weird and wonderful things. Right? We print syringe pumps, thermometer racks, centrifuge inserts, racks for pipettes, complete platform jacks. Everything that's made of plastic could actually be produced this way. And you can produce it yourself. You can design it. It can be the way you want that piece of hardware to be. Other things are possible. This is a kit that's published online. You can download it. It's made for a laser cutter, but there's no reason why you can't convert it to 3D printed parts. And if you look at the pieces of equipment here, on the left is a so-called nanodrop. These things are expensive in biochemistry labs. There's an open source digital microscope, centrifuge made out of a hard drive, a PCR machine. I know not everybody is a biochemist, so this doesn't mean all that much for the non-biochemist. But this is basically everything needed to run pretty much every biochemistry track that we are doing. And this can be produced out of very cheap board and a handful of electronics. Just imagine the possibilities in terms of outreach to the high schools with this type of stuff. There's a microscope designed by the University of Cambridge that's completely 3D printed and takes a very cheap Raspberry Pi camera, inverts the lens, and they do research on this. I don't know about you guys, but if it's good enough for the University of Cambridge, it's certainly good enough for me, right? And in case anybody wants to comment that the quality is not high enough, they do it to check bacteria in the water of the River Cam. So this is a digital microscope that wouldn't cost you more than 700 rand, right? And the closest closed source microscope would set you back about 100,000 rand, just to illustrate some of the concepts. But what do we do? As I said, we're printing all kinds of weird and wonderful things. One of the things that we built is a syringe pump. I just stole this one out of my own lab. This syringe pump would cost you about 30,000 rand if you buy it. But if you have a look at it, it's basically a stepper motor with a piece of metal and some printed junk around it. Right? Those stepper motors cost you about 250 rand. Everything else will cost you a handful of money. So for about 500 rand, you can get a stepper motor with a controller box and everything. And you can do your syringe pump. You can do your reactions. Then we print a reactor. This is printed from inert plastic. We do the reaction in so-called flow chemistry. And this paper has been accepted just now. So other people think this might be an idea as well. But so this is the first iteration of a syringe pump. We've got more advanced syringe pumps now. I know the picture is not very pretty. And we've built a controller box around it as well. So it doesn't have to be connected up to a computer. You can put this anywhere, and this would cost to purchase commercially 120,000 rand, right? 4 syringe pumps at about 30,000 rand each. And we built this for less than 5,000 rand. Just to give you an idea of what is possible. We're doing flow chemistry. These are reactors. This is within the chemistry sphere disruptive technology, where you take a reactor, and I've got one over here, and you can see that it's got small channels in there, and you do the reaction in these channels. The benefit of this is that you can do continuous production of your product. Right? So rather than doing it batch-wise, you can now do it continuously. So if you want 1 gram, you run it for an hour. If you want 10 grams, you run it for 10 hours. So this opens up production possibilities worldwide. What else do we do? We've done some experiments where we modeled a die, then printed the same die, filled it up with something which would be clay-like for those non-chemists, and then hardened that clay-like material and melted the die away. So we've got this porous block of material, and we stick a catalyst on it and do our reactions. And that works. This has been submitted by now. And then I thought, but wait a minute, this is not good enough. Let's just design a reactor around it, print the reactor, insert the actual catalyst block, and then continue printing, and then use that in flow. And here we've got a little video of the system running, and I'll try to talk you through it. Important is you see the syringe pump, you see the rotating part there, so that's depressing the plunger on 2 syringes. The controller box tells us it's at 9,000 and 7,000 microliters per minute. Then it goes through the tubing into, that's the little reactor that we use for this thing, in a constant temperature oil bath. And then at the end, you literally collect your product. Now this can easily be scaled, not scaled up, because then you run into thermal problems, scaled out. Right? Rather than having 1 reactor, you can have 100 reactors. You can print them yourself, so it's easy enough. And then literally this size, we've printed them, that are connected up, and anybody with a 3D printer and the skills to read a paper could produce the anti-inflammatory that this was made for. Let's see, I think this is the only one that works. Right, so this is a video of what can be done in a distributed manner. The starting material comes in, and you can just buy that off the shelf. You need to do some evaporation and a reaction with some salt, and the separation. Then you evaporate the solvent again, add some more reagents, have the reaction at 0 degrees, evaporate it again, do a separation. The one phase you don't need, that's a side product. Filter it off to make sure that there's no gunk in there. Do a reaction. Right, another phase separation. And there's your anti-inflammatory. This is the future of pharmaceuticals, ladies and gentlemen, in my mind. This is obviously a small test batch to show that every pharmacy could make their own headache drugs. But you can take it larger, and this has also been done. And this is something published by MIT 3 years ago, 2016. This is a flow chemistry setup, ladies and gentlemen, that you can change. It's the size of a fridge. You can change it to produce exactly the pharmaceuticals that you need at that moment. And by just running it longer, you can generate more of the product. So imagine having a resistant strain of malaria, and the medicines aren't around, but the guy in the hospital just changes a couple of modules and gets the medicine prepared specially for you. This goes even so far that there's a formulation module there. Right, so that's chemistry. And I think I've lost half of you on parts of the chemistry already. What else is possible? Right, what more can be done? Let's get our imagination to run free. Remember that I showed you a picture of this thing at the start. This is a homemade CNC machine. It will cost you a couple of $1,000, and it's the size of a standard wood board. Right? So everybody thinks, what on earth can you do with a wood board? Well, you can make furniture. For the price of a piece of wood at a hardware store at Builder's Warehouse and a file that you download for free, you can tell this machine to build your furniture. And there are a couple of people that have kitted out their complete house using this technology. Okay, let's go weird, because I started talking about what is possible to help everyone, not just a couple of people that can afford this type of technology. There's an organization in the States called Open Source Ecology. This is a guy that went bankrupt as a farmer, and he decided, he's got a PhD in physics, realized his PhD made him useless for society, started farming, went bankrupt, and said, no, this is nonsense. We need to have the tools to build civilization. This is dreaming big, ladies and gentlemen, to redesign civilization in such a way that everybody has every tool that they need. To live in comfort, he decided he needs about 50 different machines, and he started making these machines. He started designing the machines, making the plans freely available. And that organization is getting attention right now. One of the machines that he's built is a so-called compressed earth brick press. To make this yourself would be, and I've done the calculations, you don't even spend 10% of the price of purchasing one. The plans are all out there, you can download them if you want to. He called it the Liberator, for a very obvious reason. This liberates us from debt, right? If you can make bricks, then you can make a house. If you can make a house and you start small and you design it properly and you put solar panels on the roof, which you can make yourself as well, and you harvest the rainwater, which is relatively easy to do, then you don't have a huge debt. Right? So if anyone with a welding machine can make this compressed earth brick, make it. If you can shovel soil in there fast enough, you can press your own bricks, build your own house. This design is freely available. The guy will teach you all the stuff. And yes, this is a relatively small house, but you can expand it to build larger houses. And it has been done. Obviously, it's cold in the States with all the snow. And on the background, you see the compressed earth brick maker. And the guy lives in this house. And because it's designed completely modular, you can start with the basic necessities and then expand it to a larger house. He's even designed an open source greenhouse with an open source aquaponic pond attached to it. So he's even offline in terms of food. So that's why I'm saying, ladies and gentlemen, just imagine what is possible with this open source distributed hardware. We can produce our pharmaceuticals, our medicine, right where we need it, when we need it. We can produce equipment cheap I've shown a couple of examples where we're at 5% of the commercial price. Furniture, houses, this is not necessary. This, absent poverty, this diverted society, this contrast is not necessary. Can you imagine?
Thank you, Professor Renaud. Do we have questions for him?
Lots of
We've got one.
Lots of thought for food.
Thank you, Greg. That was very interesting and practical. My question is one of implementation. You are a chemistry professor at the University of Johannesburg. You already have some resources. You have a lot of knowledge that you can apply. You make it sound very easy to set this up and to start doing your own thing. So my question to you would be, how easy would it be for a person without any technical or scientific background? Let's use your brick maker as an example. You say anybody with a welder could do it, right? How easy is it to use some of this technology at the moment? Because as things work, usually in the beginning it's more difficult and then it gets more easier. So how easy is it in your view at the moment? And then secondly, okay, let me just ask that question first. Okay, how easy is it?
So it's probably more difficult than I think it is. I think the way forward is to start here at a university. Start with 3D printing. It's been shown numerous times that you can recoup the cost of your 3D printer within a year's time by just printing one item per week for your household, right? Whatever you need, something to put a spoon on or whatever. So that would give a little bit of economic incentive to actually start working with these 3D printers. In my mind, the second step would be then, let's print one of these CNC machines. You can buy everything else in a kit, and the last bits and pieces are literally metal tubing that a company in Westdean is making and selling. Right? So it's possible. These things, run workshops that teach you how to make the machine and teach you at the same moment how to run a workshop teaching how to make the machine. Right? So that would mean we need a couple of people to go there, learn the skills of a brick maker in this case, and then start teaching people. So yes, there is an initial speed hump, I would say. We need to go through a relatively steep learning curve, but that doesn't make it impossible. So the idea is literally put a roof up somewhere and a couple of welding machines, get somebody with the skills to teach how to make these machines, and then start moving from there towards a house, towards whatever we need.
Okay, thank you. And I think my second point or question has to do with design. So you make these syringe presses, for example, but you need a design for the machine to build that properly for it to work. And I think part of the key here is that almost none of us have the skills to do the design. So the open source design part of this is going to be really important. And I would venture that part of the role of a university would be to make designs appropriate for South Africa and make those designs freely available to the country. Because I think there's probably, although there's a lot, as you point out, I mean, I've used American recipes to try and cook something, and I can't find the products that they're speaking about. And therefore, I'm not saying the American designs won't work, they probably will, but somebody needs to South Africanize it to be sure that it will work, you know? So I just think my view would be, and I would be interested in what you think about that the design part of this and making that South African and available will be also a very important aspect to make this work.
Yes, definitely. Look, there's a tremendous amount of designs available as it is, and they're ready for the equipment. So theoretically, you could set up a small workshop for a bit of money and start producing of these things. But then the learning curve would be in going from a consumer of the designs to a producer of the designs. And that's obviously a bit of a learning curve. It's not impossible, a lot of people do it. We've done it with the 3D printing, but it takes a bit of time. But having said that, also not as much time as most people think, right? Within 2 weeks, you could be in a position of designing simple things, and from there, you can actually move into more difficult things. Incidentally, even the software is open source, so it's as much as downloading it and installing it and playing with it. So it's actually a complete open source world out there, software, hardware, ready for anyone if you just want to be a consumer and produce whatever is on the internet, or you can go design it yourself. And the costs are low. Another example is there's an open source laptop for sale. Now, I don't know, Duncan, what the university paid for your laptop. This open source thing is obviously not as strong as the average one that we get these days, but it comes with a price ticket of $100. That's 1,500 rand. So for somebody who just needs to write their prac report on a laptop, that's actually a very affordable solution, rather than the, I think UJ pays 14,000 rand or something for a laptop. And so it's something that we need to think about, these opportunities. They are out there. Oh, thank you.
Thank you, Professor Reno. Quite an insightful presentation that we received from him. Makes one imagine the kind of possibilities that will exist within the fourth industrial revolution. But right now, it's time for us to break for lunch. We do have Microsoft exhibiting outside if you want to familiarize yourself with artificial intelligence and the things that could happen within the fourth industrial revolution. You're welcome to do so. You can share your experience online as well. Please use the hashtag winterschool4IR. And then lunch is 45 minutes long. We will be back in 45 minutes. So it's 12:15 now. So by 1 o'clock, if you could be back, that would be great.